Happy Physics Friday! The other day, my roommate and I were walking on campus, and we passed a chain like this one right here. And I, being me, mentioned that the shape of these chains are pretty cool. And he responded, yeah, they are cool. They're pretty cool parabolas. And I said, what do you mean parabolas? And we got into a bit of a back and forth on what the shape of these chains actually are. So the goal of this video is to settle our debate and figure out what the shape of this chain actually is. So let's get to it. So you might be wondering why I'm convinced that the chain we saw earlier, even though it has a parabolic shape, it isn't a parabola. And the reason is as follows, right? The chain is going to minimize the gravitational potential energy. So to put that into math terms, if we write some sort of Lagrangian, right, our total potential energy is going to be mgh, right? But we have a chain, right? So we need to integrate over its shape for the entire energy. So we can have the integral of y and then just ds, where ds is just over the shape that the chain makes. Now, the interesting thing is that this isn't the only condition we have for this, right? We also have the fact that this right here, the arc length of our chain, is going to be constant. Our chain, it's not some special metal or like slime where it's like, changing with gravity. So this right here is just going to be some constant. We're going to call it L. And if you notice these two things, and you're somewhat familiar with like the calculus of variations, you can see that we can combine this into, we can use the Lagrange multiplier for this, and then just use the Euler-Lagrange equations to solve for the shape of the chain y. So let's go ahead and do that. It should just be noted that ds right here is equal to just the square root of 1 plus y dot squared dx. Typically, I know the dots are typically reserved for time derivatives, but I don't want to be writing prime squared. It just looks weird, so I'm going to be using the dot. So at any rate, incorporating Lagrange multipliers into both of these things, we end up with the integral of y minus some lambda and then ds, right? And this ds is obviously this right here, so we can go ahead and write it out completely. So y minus some lambda, and then square root of 1 plus y dot squared dx. So now all we have to do is use the Euler-Lagrange equations. We can solve for y. So let's go ahead and do that. The usual form that the Euler-Lagrange equations take is, the usual, partial Lagrangian with respect to y minus the, d over dx, and then partial Lagrangian with respect to, y prime. That's the usual form they take, but whenever there's no explicit x dependence, you can actually show that the equations take a different form, namely that y dot times your partial derivative of the Lagrangian with respect to y. With respect to y prime, or y dot in this case, minus your Lagrangian is just equal to some constant. So using this right here, all we have to do is really compute this right here, which isn't too bad at all actually, because if we just differentiate this right here, we end up with y dot over the square root of 1 plus y dot squared, where the 2 in the denominator is canceled by the chain rule of the 2 in this exponent right there. So we end up with y prime squared over the square root. Should do that. Okay, plus 1 plus y dot squared, and then times y minus lambda minus just the Lagrangian itself, right? So just this bit right here, y minus lambda times square root of 1 plus y dot squared is equal to some constant. I'm gonna just call it a, right? And now what we can do is just rearrange this and get a nice differential equation of sorts. So we can just integrate and solve for y. So multiplying both sides by this right here, we end up with y dot squared, y minus lambda, minus y minus lambda times 1 plus y dot squared equals some constant a times 1 plus y dot squared. Okay, and we can see that some of these things are to cancel, right? So we see that, yes. Okay, those yes, those terms cancel. So we have minus y minus lambda, then equals a square root of 1 plus y dot squared. And now we can go ahead and just solve for y dot. So I'll move that over here. We have then y minus lambda all squared minus 1 is equal to y dot squared. Yeah, it is equal to y dot squared. So then all we have to do is just say, well, now we have this dy over the square root of y minus lambda over a squared minus 1 equals then just some dx. And we're obviously integrating over both of these. So here's going to be some x and then plus c. But we're actually just going to call this c0 because our data is going to, we can just send our data to be 0. So the shift in the x, there doesn't have to be any. So we can just eliminate c right off the bat. And all we have to do now is evaluate this integral right here, which really isn't bad because the integral of 1 over the square root of x squared minus 1 dx is equal to inverse hyperbolic cosine. So I'll write that as cosh inverse, right, of x, right? So all we have to do is really just include this a in there and just do a reverse, just add an extra term out front to account for the fact that there's an a. So that means we have inverse hyperbolic cosine of y minus some lambda over a. And then, well, whenever we differentiate this, we're going to get an extra a out front, right? So we just throw an extra a to cancel, right? And that right there is just going to equal x. So then we're going to have, we just solve for y, which isn't too bad. We just have to do divide by a, so we end up getting cosh of x on a. And then times a, and then we're going to have to just add a lambda. This is our y right here. So you see more or less that we have 3 parameters right here. We have this lambda, we have this a. So you see that we have two. So you see that we have 2 parameters right here. We have this lambda and we have this a right here. We did have a c, but we did just assume the shift in the parabola to just be 0. So we eliminated that right there. So we have 2 degrees of freedom right here. So this is why my argument is that this right here is just that the shape the chain makes is just hyperbolic cosine, you know, for this argument right here, right? Now, it should be noted that if the chain is shallow enough, right, that this right here can actually approximate a parabola. So, you know, if you use the Taylor series for hyperbolic cosine right here, what we end up with is just, you know, lambda plus a, right? That's just going to be the first term. And then we're just going to have plus x, what would be that coefficient? I think that'd just be 1 over 2a. Yeah. Yeah. And then you just have 1 over 2a times x squared. So really, it can be a parabola if it's shallow enough. But yeah. So our chain can approximate a parabola if it is shallow enough. So what we're going to do now is actually get the measurements and the data for the chain. And from there, we can actually see which model, even though they're sort of the same, we can see which model is actually better. So let's hop into Microsoft Paint 3D. So the way we're going to determine the distance and the actual shape of this chain is going to be by counting, and by counting I mean using Microsoft Paint, the number of pixels each chain takes up. So if we start from one point right here, we can drag and find the coordinates in pixels at least relative to this point right here. So it's 416 away in the x direction and 120 in the y direction. And from that, we can determine the actual shape of this chain. So on that note, cue the montage. So just looking at the models fitted to the data, it's hard to see a difference between the two. And if we actually look at them, we see that there's hardly a difference in their r-squared values. So at the end of the day, it doesn't really matter, at least for this chain, because it is a bit shallow, it doesn't really matter if you choose to model it with a hyperbolic cosine or a parabola. The effect at the end of the day is really the same, and it's nearly impossible to distinguish the two. An interesting thing to note, though, is that because they're so similar, if you actually just approximate the hyperbolic cosine right here as a parabola, you get more or less the exact same thing as if you model it with a regression model right here. So this 1 over 2a is this constant right here, which is more or less what a1 is right here. So again, doesn't really matter too much. So I suppose my roommate and I will just have to agree to disagree, but at the end of the day recognize that they really are the same thing. At any rate, thank you all for watching this video, and I will see you in the next one. Bye.